Force is something that pushes or pulls another object and can cause the acceleration of the object it acts upon. Net external forces cause acceleration of objects. When the net force of a system is equal to zero, there is no acceleration within the system and it is at equilibrium. In a system where force is present, an agent causes or produces the force, and then the object is the recipient of that force and may experience an acceleration. Just like when Jake pushed me, he is an agent and I am the object. Forces like tension and friction happen because things are touching, so we call them contact forces. Forces like gravity and electromagnetic forces can be felt even if you aren't touching the source. We call these long-range forces.
Let's compare the different types of forces and what different situations we see forces appear in. The force of gravity on an object can also be called its weight. It is calculated by taking the mass of an object and multiplying it by its acceleration due to gravity, or little g. The force of tension on an object happens due to a pulling force, usually observable when things are held or pulled by strings or rope. The force of tension acts equally on the object and the string. When an object is hanging in equilibrium, the sum of the forces in both the x and y axes must be equal to zero. The normal force is the force that acts upon objects when they are placed on a surface or another object. The normal force always acts perpendicular to the surface where the object rests or is forced upon. It is a contact force that is most commonly defined by the object's weight. For example, I am standing on the ground right now, and as much as my force, gravity, pushes down on the floor, the normal force will push back with an equal amount. If the forces were not equal in magnitude, I would either be falling through the floor or flying into the ceiling. Another example is a block on an incline. In this case, the normal force will not equal to the object's force of gravity. The incline causes the object's force of gravity to be visualized in components, and only the component of gravity acting perpendicular to the surface of the incline is equal to the magnitude of the normal force. The force of springs depends on the spring constant, or K. The force of a spring is a restoring force because the spring produces force. Its energy oscillates between kinetic and potential. The force of friction is a contact force and always acts opposite direction of motion. Friction causes drag in motion or acceleration in the opposite direction. Friction is determined by the coefficient of friction and is based upon the material that is present. Static friction is present when there is a force, but not enough to cause acceleration. The force of static friction is equal to the applied force until it reaches a maximum value, where the applied force overcomes the maximum value of static friction. Static friction is compared to kinetic friction once the object begins to accelerate, and kinetic friction is calculated by the object's normal force and the surface's coefficient of friction. The closer the value of coefficient is to 1, the rougher or more friction-inducing the material is. The closer the value of coefficient is to 0, the smoother the material is. Static friction is always greater than kinetic friction.
Considering objects and systems. Do. Be aware of how the system is defined, whether or not the Earth is included. Visualize the system in components when setting up net force equations. Consider the direction of motion and the direction of any given applied force. Know that if an object experiences a net force of 0 and is in equilibrium, the forces in the x and y axes must cancel. In a rare case, if an object's net force is equal to 0, this does not mean it is not moving. An object with constant velocity, therefore no acceleration, can have a net force of 0. If an object experiences a net force not equal to 0, it is experiencing inertia. Here are some examples of systems: a person in an elevator, an Atwood machine, a pulley attached to a table, a pulley attached to an incline. Let's talk about force vectors. Vectors are measurements with a magnitude and a direction, so it is easy to understand why forces are vectors because they push or pull in an observable direction with a certain measurable force. Force vectors represent the magnitude of a force, so if the magnitude of the applied force is greater than the force of gravity, the force vector of the applied force should be longer. Contact force vectors should always be drawn perpendicular to the contact point. Force of gravity force vectors should be drawn from the center of the mass to an object, not simply from the top or bottom of it.
The three laws that are named after me, Newton's laws, outline the effects of constant forces and the objects on which these forces act. My first law states that an object in motion will stay in motion, and an object at rest will stay at rest unless acted on by an external force. This describes inertia, the property of an object to resist changes in its state of motion. This is known as the law of inertia. Common misconceptions with Newton's first law include the thought that contact forces persist even after the contact ceases, or that forces must persist to cause motion in the given direction of motion. This is not true because a motion at a constant velocity does not require an outside force. This supports the fact that an object equilibrium, which has a net force of 0, can be in motion. My second law bears the extremely useful equation F equals ma, or a statement of acceleration of an object depends directly upon the net force acting upon the object and inversely upon the mass of the object. Acceleration is always in the same direction as the applied force, but this does not mean that the acceleration and the force are in the same direction as the motion. For example, think of a car hitting a brakes, yet still moving forward. The direction of motion is forward, but the direction of force and the direction of acceleration are backwards. My third law states that for every action there is an equal and opposite reaction. This means that the forces of an object in contact must be equal to the magnitude and opposite in direction. They are also acting on each other, not the same object. Remember, this law allows for the existence of action-reaction pairs, where interacting forces can never balance one another since they act on opposing objects. Here's an example of action-reaction pairs in Newton's third law. Think of a bug hitting a heavy truck on a highway. The net force of the bug on the truck is equal to the force of the truck on the bug, because of my third law. If there are any questions, just know that I'm right and you're wrong. Newton out.
Let's review inclined planes. On an inclined plane, total energy is converted from potential gravitational energy to kinetic energy as a block slides down the ramp. But let's stick with the dynamics of inclined planes. You will most likely see a question regarding how far up a ramp a block will go if released with a given velocity, or something regarding how much force it may take to push or pull an object up a ramp. Make sure to check whether or not there is an applied force and whether friction is negligible or not. Remember that the normal force will not be equal to mass times gravity, but it will be a component of this value, and it will depend on the angle of the incline.
When there are two or more objects acting on each other, they are considered compound bodies. Some of the examples we know best is a table with two blocks hanging off of it, or multiple blocks stacked on top of each other. In one of these systems, we can find total force, gravitational force, tensional force, frictional force, normal force, system acceleration, and lastly, the mass of each object. Inertial mass is calculated by using Newton's second law, F equals ma. We define a measure m, so m equals F over a. Gravitational mass is calculated by using the gravitational force, or big G equation. F equals g mm over r squared. As far as we know, there are no differences in an object's values for inertial mass and gravitational mass. Therefore, we only have one defined mass for a given gravity value, but it is important to note the differences in how these masses are derived.
Another force is centripetal force. It is a special force because it only appears to act on things in circular motion. In a swinging object on a rope system, the tension of a string that holds the circular object in a constant path is equal to the centripetal force acting towards the center of the object's orbit or circular path. Centripetal force, Fc equals mv squared over r. Centripetal acceleration, AC equals v squared over r. Velocity and centripetal velocity is Vc equals 2 pi r over t, which stands for period. There's something that could be said about one's apparent weight while in circular motion. For example, if your car turning a bank, you feel pressed against the car when turning right, and you feel as you're leaning when you're turning left. This is because of centrifugal force, and it is a non-real, meaning it cannot be measured or defined, product of centripetal force.